All right, so that was problem number 47. So now let's do 49. So let me read this out loud. For problem number 49, it gives us a picture, and I'll draw the picture on the board, but it says a mass M descends a vertical distance from rest. Okay? And we're going to ignore friction and the mass of the string. And it asked us, from the conservation of mechanical energy, will the linear speed of the descending mass be greater than or equal to or less than the square root of 2gh? Why? And then it gives us a mass to plug in and all that stuff. So the figure, I guess we have to draw the picture in order to do it. The figure is figure 2823, which is somewhere in this book. If you guys find it before I do, please let me know what page it's on. I'm almost there. Figure H. Oh, I see. All right. So let me draw the picture. So there's a pulley. We have a pulley like this. And to draw the picture as it is in the book, we have the mass of the pulley here. And it has a radius, capital R. And we have an angular acceleration, alpha. And that pulls down with a tension force. And that's hooked up to a mass. And then the force of gravity is being applied, which is mg. This also has a tension force, which is equal to t. And then this will have an acceleration, which is equal to g. Now what this does is this creates a torque force. Right? It has a positive torque force in the xy direction. And so based on this figure, the question that they're asking us, and let me go back to the question now that you have the picture there. The question that they're asking is, the mass M descends a vertical distance from rest. If we ignore the weight of the rope, because technically there's a rope that's kind of wrapped around the pulley like this, and it has a weight, and we should, gravity acts on the weight of the rope too. And then it says ignore the friction of the pulley, so there's going to be some friction, some moving parts touching. If we ignore all that stuff, because the conservation of mechanical energy, will the linear speed of the descending mass be greater than, equal to, or less than the square root of g? Why? So now to solve this, it should be less than this. So it should be option number 3, which is less than the square root of 2gh. Now if you don't remember where that comes from, just to kind of remind you guys, we said that the potential energy is equal to the mass times the acceleration times the height, right? And then there's a relationship. The kinetic energy is 1/2 times the mass times the velocity squared, right? And so if I take an object at the top and I hold it like this, so forget about the pulley for a second. I have a block that has a mass. When I raise it up, I have potential energy. When I let go of that block, it will fall. The potential energy that's stored in that object is this. When I let go of that object, eventually all that potential energy is converted into kinetic energy, so at the very bottom, just before it hits the ground, I'll have full kinetic energy. That's what we're trying to establish. What is the relationship? So what we have here is that U should equal K, or the mass times gravity, the acceleration due to gravity times the height should be equal to 1/2 times the mass times the velocity squared. The masses cancel. I multiply both sides by 2, and I get 2gh is equal to v squared, right? You guys see that? And then what do? Take the square root of both sides. So I get this and this. So the final velocity should be equal to 2gh. If it was a straight linear conservation of energy problem, that would be the relationship between the two. Okay, and I don't know if we did a lab on that. We cranked through that whole thing, but just to refresh your memory, that's where it's come from. And what they're saying is because they have a pulley and there's a torque, would it be equal to that? Would it be greater than that? Or would it be less than that? And the correct answer is less. And now we have to explain why. Okay? Why? Well, if it were a point mass, then its speed would be the square root of 2gh. However, the object has a rotation. So it has rotation kinetic energy. So its kinetic energy is not this. If it was a point mass, that would be the kinetic energy. So rotational kinetic energy is different because every particle in that object of that pulley as it rotates around, some parts are closer to the center and some parts are closer on the perimeter or the further radius out. And that's kind of why we have to make a different calculation. So the kinetic energy, so the conservation of kinetic energy for rotational energy looks a little different. It would be like this. It would be 1/2 times the mass times the velocity squared. That's the initial, right? Plus the rotational energy. 1/2. Now remember, rotational kinetic energy or potential energy is the moment of inertia. Now this is why it's different. Times 0 squared plus mgh. So that's the initial. And all that's going to be set equal to, so that right there is the initial. So then the final would be 1/2 times the mass times the velocity squared plus 1/2 times the moment of inertia times the angular speed squared plus mg of 0, right? So this is the initial energy, and that's the final. That's the kinetic energy. It has no velocity at first. This is the rotational kinetic energy, which is based on this formula right here. Well, the pulley hasn't started rotating, so it has no angular speed at first. That's 0. Then the potential energy due to gravity. So this is equal to the second line. Now, the final velocity is v. The moment of inertia times the angular speed squared times 1/2 is the rotational kinetic energy, and then our potential energy is 0 because it'll hit the ground or it'll stop rotating. So this goes away, and now we have from the initial mgh. So if I think of this in terms of the initial and the final, because that's what conservation of energy is, the initial should equal the final. My initial is just mgh, because everything else, because there's no motion on the other side, there's nothing. But my final is all this stuff, which is 1/2 times the mass times the velocity plus 1/2, right, times the moment of inertia, right? And what is the moment of inertia? Do you guys remember? Well, it depends, but because it's a pulley, we'd have to go to whatever page that is. What page is that? 284, I think it was. And it's a cylinder disc, so it's 1/2 mr squared, right? So the moment of inertia would be 1/2 capital mr squared, right? And then times the angular velocity squared. All right. So we've got to do a lot of work to clean that up. Now, one thing that I can do is I can remember that this is equal to V divided by R. So I could switch this in terms of angular velocity is really the tangential velocity times R, but we square it, so it's V squared R squared. Okay? And so when I write it that way, guess what happens to the radiuses? They cancel. Okay? And so if I clean up this other side, I've got mgh is equal to 1/2 times the mass times the velocity squared, and then this plus 1/4 times the mass of the pulley, big M, times the velocity squared. See how that works? Cancel all the H or all the M's. Well, you cancel it. Well, you can't cancel it out, can you? No, that doesn't work out, does it? Can't cancel it out. Okay, we're almost done. Just stay there. Don't leave. We're almost done. So then when you plug everything in, if you solve for V, you get V is equal to the square root of 4mgh all over 2 little m plus big M.